Today what we will start on is an important area of statistical mechanics, important both for physics and chemistry. And as I keep telling you that these are fairly regularly taught in most places in the world, at least in serious places. Now, why these things are important is the following. Till now we have done ideal gases, and ideal gas the particles do not interact, though they have many interesting properties and particularly useful expressions like entropy, specific heat that we use later. However, a system is interesting because they have interact with each other, they undergo phase transition. An ideal gas does not undergo phase transition. You plot PV, P against V, 1 over V, it just never shows any bend. Like if I plot P against 1 over V, then remember it is a straight line, and this is the, that is how it goes, okay. That is where universal gas constant was found out. Real world, however, when you high temperature it is something like that, but when you go to low temperature then it undergoes a phase transition, and this is gas, this is liquid, and then it undergoes one more phase transition, is the crystalline state. So, these breaks and this is the coexistence are because the phase of the system goes discontinuously from gas to liquid to crystal. An ideal gas which does not interact does not show the phase transitions, it just goes on linearly. When people started looking into that, then what the first thing that you find that was noted by van der Waals, that if this is the ideal gas which was known long time, then in a dense gas, when density of gas, I will little bit quantify what is the density because it is very important, then it starts deviating from the A, then it goes like that, but it starts deviating from the ideal gas behavior. So, this is the ideal gas, which is PV equal to RT. This is the real gas. It undergoes at a lower temperature, it undergoes phase transition, but you do not need to talk about it right now. We will talk about it at length, but right now let us see that we are just not that low temperature, we are intermediate temperature, but we start seeing the departure from the ideal gas behavior. As I said, this was observed by van der Waals and many other people. So, the people then tried to explain this. It was clear very early that this is because of interactions between atoms and molecules. Now, in order to talk of interactions, I need to talk of a separation, length scale between two things, and the way we talk is introduce a dimensionless quantity rho star, which is number of particles in a volume V, then cube by the molecular diameter, and these, so sigma is the molecular diameter. So, n sigma cube is kind of a fraction of the volume occupied by molecules. So, this gives you a measure that if I have these kind of molecules and if this is sigma, then pi by 6 sigma cube would be the volume each one occupies, then you get a measure of that. So, in the roast, and roaster is very significant, by making it dimensionless we get some very important what is called the convergence. For example, the roaster typically in the liquid is between 0.8 or 0.85 to 0.95. Gas is between about 0.1 or so. So, in between these gas and liquid, there is a huge coexistence which really takes you from 0.1 to 0.6 or so. These are very important numbers. Why it is important? Because now I tell you some numbers like water roaster is 0.76, then acetonitrile I think as per I remember something like 0.85, methanol little bit more dense, it is about 0.9. So, in a very small, so when you in number density, if you look at them, number density this part varies quite dramatically from one liquid to another liquid, even of the order of 1 order of magnitude. But however, when you do the roaster, there is an universality that appears. The universality is that this is that we have a suddenly a dimensionless quantity to characterize the liquid. Okay, now I have a number, I can put okay, this is the density roaster where I have a liquid, this is where it is. I do not have to talk of those numbers like 10 to the power 22 or a density of water 10 to the power 23 per cc. Those kind of big numbers are really does not make many sense to a scientist. A scientist must make them understandable, something we can grasp, we can kind of think. And these roaster also at the same time is a kind of a fraction, is proportional to the fraction of the total volume occupied by the molecules or atoms if I consider them as hard spheres. They are not hard spheres, but there is a big repulsive potential, and because the rough potential you have size. And that is why Pauli was fond of saying that that he created the solid state or condensed matter physics because of Pauli exclusion principle and all the you have the hard repulsive part of the potential, and solid exists because of that hard repulsive part of the potential. Pauli was known for making many interesting jokes. Okay. So, this is an important thing that the number density. Now, as I just said in the ideal gas which we derived last 2-3 lectures, that we have these expressions. They are very nice expressions, but they are not, they cannot explain phase transitions. Phase transitions exist, as Pauli also said, called condensed matter, because particles interact. You and me, we exist because we interact. For some people it does not bother that whether you exist or not, or you know, or why you exist, but for some crazy people it is important to know why you exist. So, these teaching in India, which is a very what based, I remember our school questions were always, what is this famous for? What is the capital of Hawaii or whatever? What is the capital of Madagascar? So, what are the important goods made in Nigeria? It is all about what, and you go very far by just doing what. We do not say why, and why these things happen, why you get this particular fruit in that Mediterranean. Then come even deeper level is how it happens. So, see, you know, Feynman's, you must be joking, Mr. Feynman, there is a very interesting chapter you should read. Richard Feynman's father was a salesperson. He wanted to make his son a scientist. So, whenever he had time, he was at home, he would make scientific toys, and then he would take his son into the park. There little track, mountainous region, he would go and he would teach them, this is the bird, that is this is bird, that is bird. And then I think Feynman was always a show off, right? So, he showed up little bit, and then whole locality every father and mother started taking their children out for trekking, and then they all knew names of every bird or everything. And they now in turn asked Feynman, hey, do you know the name of that bird? And by that time Feynman forgot it. Then Feynman's father told him a very important thing, which Feynman said was important all his life, that the name is not important. It is important that what it looks like. It is important this kind of bird does this kind of things, and you find in this area. So, many of our education system is this what based. We do not even go to why, and then of course how is little far. So, coming back, we are now going to ask a few questions, why a phase transition takes place and how do we explain that. So, this is a long and very, just like chemical reaction dynamics, which has got probably one of the most celebrated theories and most celebrated Nobel laureates coming from Rudy Marcus, Herzberg Poliani, or Ahmed Zuel and many others, who recently essentially the paper of 1976 which gave Leavitt and Warshel Nobel Prize was also essentially doing enzyme kinetics. Now, in physics and also part in physical chemistry, this equally respected and celebrated is the phase transition and the condensed matter. So, because that is how materials form, and now that is how we understand how something forms. Then of course, thermodynamic properties are important, like compressibility as we discussed and other resistivity. Then come of course electronic properties, which somehow people are more focused on, but you have to make the material first before you study electronic properties. So, basically why and how the phase transition occurs, the gas, liquid, liquid, solid. So, this is the question that we will be asking today and next few lectures. Now, as I just told you, how do we go about it? I told you that ideal gas does not have a phase transition because there is no interaction between them. So, phase transition is a consequence of intermolecular interaction. Actually, everything is interesting is in intermolecular interactions. So, let us first define what I mean by intermolecular interaction. The simplest one, or one of the simplest one, is intermolecular interaction Vr. R is the separation between two molecules. I have the simplest thing in mind. There are two molecules and there R is the separation from center to center, Vr against R, and I have, this is the one a short term part of that, this I call molecular diameter sigma. This is harshly repulsive. Remember Pauli's comment, this is because of electronic overlap of the electrons, electron density. This is an attractive part. Hard sphere itself is a very interesting system, and in statistical mechanics, huge amount of study goes on just to study the hard sphere part. But that hard sphere part is not really realistic. Like this is this potential called Lennard-Jones potential explains properties of noble gas very well. That is what the first kind of things that people developed. So, this Vr is written as, these are the things I will be using. This is called Lennard-Jones 612 potential. This is the repulsive part, that is very short range and diverging, and this is the attractive part. This is the part which is given by this minus sign here. So, this is the one of the simplest interaction potential. Okay. Now, with phase transition due to interactions, and if this is a kind of interaction potential I am having, and that is what I was mentioning to you, even at a two body potential I cannot solve Newton's equation. I can reduce it to a quadrature, and three body I cannot solve at all. That is why we need to go to statistical concepts. I am now keep a little bit of that upstairs, but then I am going to do the rest of the how do you go about doing statistical mechanics. So, I keep VR equal to, let me just keep this one, that is enough. Okay. So, we cannot do this. Now, how do I start about it? I want to consider a number of molecules at volume V at temperature T. I want to work in canonical ensemble, and now I want to calculate the partition function of this quantity. So, statistical mechanics tells me if I want to calculate free energy, I want to calculate the equation of state, pressure versus density, I have to work in one of the ensembles. Microcanonical ensemble in this case is incredibly difficult, that because the constraint of constant energy does not lead me to any easy, is not amenable. So, canonical ensemble we can make some progress, grand canonical also we can make progress, but this is the one historically, as I told you before, you work. And canonical particle means I have a system with a total number of particles n which are interacting among themselves with this potential, I put them in a volume V and at temperature T. Now, if I decrease the volume or decrease temperature, this system from gaseous state would go to liquid, then to solid. And how do I describe this sequence of phase transitions? How do I decide that at what temperature or density a gas, water for example, we know at 100 degrees centigrade an atmospheric pressure goes from steam to liquid water, and then 0 degrees centigrade goes to ice. What determines it? What determines this temperature 100 degrees centigrade or 0 degree centigrade? What determines water goes into hexagonal open structure? What determines iron goes to FCC, and what determines sodium goes to BCC? And what determines when you form nanoparticles, what are the size of the nanoparticles? So, these are the questions, and you can understand this when you start asking why and how. Life does not remain that simple anymore. It's probably much easier to mix A and B or some sample together in a solution, put in a bomb. I know one of my colleagues puts in a bomb, I know what actually some kind of glass jar, and they increase the temperature and they get nanomaterial and they get a paper, which is not a bad way to live actually, because here you have to think and hard. But I told you always that the famous story, one guy was trying very hard to climb Mount Everest, and then one of his colleagues was lazy and he said, why do you want to climb this one? You know, you can be easily like me, lying on bed. Why do you want to climb that? That his great answer was that, no, it is there. It is there, so I have to climb. Now, I now start this climbing. So, we have already introduced the notation. I am always a bit about 3n or 3 by 2, I think 3n. Then I have to integrate, remember I have to integrate over all the positions. Then I have to integrate all the momentum. If you have any problem, you will please let me know, because I have this constraint here, which is the Hamiltonian, right? And Hamiltonian is sum over, I assume all of them same mass, I equal to 1 to n. Then I have interaction potential, U, n particle interaction potential, that depends on R. This is a notation I told you, which means it's depend on n particles. And U, interaction potential then is depending on your V. I tend to, I like U because V most of the time is not, we reserve for velocity. Uij, Rij, I less than j. this notation, or you can put ij both from 1 to n. If you do that, you have to put half to avoid double counting. So basically this is my system n. One, 2, 3, 4, 5, and so I am having interaction between 1 and 2, 2 and 3, 1 and 3, 1, 4, this, all these interactions. So this U is sum of all the interactions. Okay. The kinetic energy and potential energy. Now we immediately note one thing, that in a classical statistical mechanics, quantum is difficult, but in classical statistical mechanics, this integration of the momentum is a trivial part, because these are nothing but Gaussian integral which we did before, and it does not overlap with position at all. So I can do the A integral part, momentum part, and then write rest as another function, which then would involve integration over the interaction potential. Okay. This is the game. So basically this is the, let us little bit summarize, fully micro analysis of interacting many body systems that we are trying to do. Starts with a given intermolecular potential. In our case, we are assuming it 12 energons, does not matter, you can do anything you want. What we are going to develop is a graph theory of liquids and gases. This was introduced by Joseph Mayer, and then it went into quantum. Actually many of the quantum things that people do, R-cell expansion, then the kind of many cluster expansion, couple cluster and all the kind of things, it was basically started in StatMech. Even before all the Feynman graphs and all these things happened, it happened 1937 that Joseph Mayer formulated the theory that we are going to describe. It is a very pretty theory, very nice and beautiful theory, and has tremendous insight into it. We will derive a expression of the partition function, we will derive the molecular expression for virial coefficients in terms of intermolecular potential, we will go towards the radial distribution function and microscopic nature of gas liquid condensation. It has been attempted by many people to go to liquid to solid, that does not work. So why? But it gave rise, this theory gave rise to the most successful theories of liquids that we know today, that are in all the textbooks. So this is the partition function, and what if we can evaluate that partition function, I can get the free energy, and if I can get the free energy, I can get the pressure as a function of volume, and that is called the equation of state, and that should show the phase transitions in the presence of interactions. And then this Hamiltonian, which is to be integrated over with the Boltzmann factor, is given by kinetic energy plus total potential energy, and total potential energy is here, and this is another notation that we use, where you already put that. I show you have a 1, 2, 1, 3, 1, 4, then 2, 3, 2, 4, you do not have 2, 1 because you have this constraint that j has to be greater than I. So the one that comes later has to be bigger than, that is a way to arrange. This kind of arranging we do in theoretical research repeatedly everywhere. Okay, now, so this is what I have been telling, that we now do that, the full thing in full glory, and this integration is that I can now carry out that we did in monatomic gas, ideal monatomic gas, this is exactly. So in ideal monatomic gas, this part is 0 because molecules do not interact with each other. Then I only have this integral to do, and that is what it comes here, and that is what de Broglie wavelength by taking h. Yeah, check me on that. I always remember h, okay, h bar, but okay, that go in there, and de Broglie wavelength. So when 1 over n factorial lambda to the power 3n. But main important thing that set aside, main important then the effect of interactions is in the Zn. We are following in toto Mayer's 1937 notation. This is called the configuration integral, or from Mayer's configuration integral. Some things in our science get less credit, and as I was telling you that in the folklore and in the terms of the huge contributions, another person we hardly talk about is Willard Gibbs, who single-handedly did so much. Similarly, the one person Mendeleev, that is considered to be, we do not celebrate enough. Another person who did his enormous amount contribution is Joseph Mayer. Okay. So, now this is the, then I am going to play certain tricks is the following. I notice that this quantity, which is sum in the exponent, now sum in the exponent can also be written as a product, right. Sum in the, here you understand, no, that this is u and u is the sum. So, sum in the exponent is nothing but a product. Okay. So, now and the product is there all in all, when all these things they are n into n minus 1 by 2, correct. Okay. So, this is I can write that quantity as that quantity, right. Okay. Now comes a very important thing, that look at this thing now, e to the minus beta u, and look at this my potential. So, when r goes to infinity, then if ur goes to 0, then this quantity goes to 1, and this is, I will now decompose that. When I decompose these things, I will find that a very large number of terms comes in. So, this is a problem, that is why I introduced a Mayer F function, but let me go through this. So, we will go to this now. So, uij. Okay. Now, this is the sum over all the particles, which I am now writing as product of e to the power beta u I j and I j. Okay. These then here the difficulty I face, I am telling you, if I keep it like that, these integrals here does not converge. So, Mayer then did the following trick. Mayer, and listen carefully, what Mayer did, he said, okay, this is the difficult part. I introduce the function f, which is the deep function. Now, if I do that function, then this simple mathematical trick means that I have to replace e to the power minus beta urij here. This is a beautiful trick actually, it is two deep things that it does, and as I told you, this is essentially the start of the graph theoretical language in physics and chemistry. You bring this here. Now, this simple trick allows the following advantage: urij goes to infinity here, and e to the power urij goes to 0. But however, when uri goes to r goes to infinity, this goes to 0, this goes to 1. However, if I take minus 1 out, then when r goes to 0, this Hertz repulsive part of the potential, urij goes to infinity, e to the power minus beta it goes to 0 like here, and it goes to minus 1. But when rij goes to 0, then this goes to 0, this goes to 1, then it goes to 0. So, by this transformation, you are removing the divergence, okay, and this is allows a systematic decomposition of partition function, which is fairly trivial, but we will see how it goes to graph theory.